students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself, Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 2, which is a solution thermodynamics. So in this lecture, we are going to discuss about the partial molar Gibbs free energy, fugacity, fugacity coefficient, fugacity in pure species, and for the species in solution. So let's first discuss about partial molar property for the Gibbs free energy. So in previous lecture, discuss about the partial molar property. Partial molar property, which means property of particular component in solution. To understand this, let's consider this example which already take in a previous lecture. Let's suppose there will be a huge amount of water in which we are going to add 1 mole water. Then increase in volume 18 multiplied by 10 raised to minus 6 meter cube. So this is a molar property of water because we are going to add H2O in H2O. Now let's suppose there will be a beaker of ethanol. Now if we are going to add 1 mole water in this ethanol, increase in volume of this solution that can be given by 14 multiplied by 10 raised to minus 6 meter cube. Now let again consider one example. There will be a huge amount of water in this beaker, and if we are going to add 1 mole of MgSO4, then decrease in volume by minus 1.4 multiplied by 10 raised to minus 6 meter cube. Okay, so in all three cases, this case is for the molar property because we are going to add this 1 mole of H2O in pure H2O. Okay, so this is a molar property. Now if we are going to add H2O in ethanol, so here these both components are different. So H2O lost their identity or property in when it go to the mixture of the ethanol, and it contribute small amount of their property in a solution to make new property of that particular solution. So this type of property is known as a partial molar property. Partial molar property may be a positive or may be a negative. So this is one example for the negative partial molar property. If we are going to add 1 mole of MgSO4 in H2O, it will be lost minus 1.4 multiplied by 10 raised to minus 6 meter cube volume. So this is the partial molar volume of MgSO4 in H2O. So this is meaning of partial molar property, and partial molar property that can be denoted by m bar. So if we are going to denote m as a property, then partial molar property that can be denoted by m bar for particular component I. For particular component I. Okay, so this is a property. We can replace this m with any property such as a volume, Gibbs free energy, enthalpy, and other thermodynamic properties. So now let's talk about the partial molar Gibbs free energy that can be denoted by G bar. As I said in this slide, this is a partial molar property. So if we want to know about the partial molar Gibbs free energy, and if we want to denote partial molar Gibbs free energy, then we have to replace this m with the G. So it becomes partial molar Gibbs free energy. Now if I want to write partial molar volume, then it becomes V bar. If I want to write partial molar enthalpy, then it becomes H bar. So now let's discuss about partial molar Gibbs free energy that denoted by G bar. G bar, which means mu, or can say that chemical potential that can be given by del GT upon del Ni at constant temperature, pressure, and Ni is not equal to J. We know that partial molar property that can be m bar that given by del mt upon del Ni at constant temperature, pressure, and Ni is not equal to J. So we are just replacing this M with G because we want to partial molar gift free energy. And partial molar gift free energy is known as the chemical potential, because in first lecture we understand what mean by the chemical potential. Chemical potential of particular component is a gift free energy per particular mole. So gift free energy per particular mole, which known as a partial gift free energy, which known as the chemical potential. So this is about the partial molar gift free energy. Now let's discuss about fugacity and fugacity coefficient. The concept of fugacity is widely used in solution thermodynamics to represent behavior of real gas. Fugacity is a effective partial pressure. So can say that fugacity is a effective partial pressure of real gas. In other words, it's a idealized pressure of real gas. It has same dimension as the pressure. Usually, it's a unit atmosphere or bar. Fugacity is the one type of intensive property. Fugacity measures deviation from ideality in term of chemical potential or partial molar gift free energy. To make more clear about this topic, take example of nitrogen gas at 0 degree Celsius. So let's consider there will be a nitrogen gas at 0 degree Celsius. Now, if we are going to apply 100 atmospheric pressure on this nitrogen gas with a particular composition of air, then pressure absorbed by the nitrogen is a 97.03 atmosphere. So this is a mixture of nitrogen plus some amount of gases. So pressure absorbed by the nitrogen is a 97.03 atmosphere instead of 100 atmosphere. So this 97.03 atmosphere is known as the effective partial pressure, or can say that fugacity of the nitrogen. Okay, so this 97.03 atmosphere is known as the fugacity for particular component, which is a represent deviation from ideality. Fugacity are determined by the experimentally or estimate by various methods. Fugacity measures deviation from ideality in terms of chemical potential or partial molar gift-free energy. We know that gift-free energy equation or fundamental property relation for gift-free energy that can be given by dg is equal to vdp minus sdt. At constant temperature, above this equation becomes dg is equal to vdp for 1 mole of ideal gas. Under gaining the same change in temperature and pressure, the equation becomes dg of ideal gas is equal to v of ideal gas into dp is equal to RT upon P into dP. So can say that dg ideal is equal to RT ln P. This P upon dP becomes d ln P. So this equation becomes like this: dg ideal is equal to RT into d ln P. So this is becomes our equation number 1. This equation number 1 given for the ideal gas. For real gas, change in gift free energy that can be denoted by dg is equal to RT into d ln F, where this pressure is replaced by the fugacity for the real gas. So for real gas, pressure can replace with fugacity. So this is how we can use for fugacity, and this is the equation for the fugacity. For ideal gas, fugacity exactly equal to pressure. So can say that F is upon P is equal to 1 for ideal gas. But for real gas, pressure that can be replaced by fugacity. At lower pressure, most of gas behave ideally. So fugacity may be replaced by pressure, hence fugacity expressed by for lower pressure that can be given by, let's take limit pressure tends to 0 or lower pressure. So fugacity upon P is equal to 1, or can say that F upon P is equal to 1 as pressure goes to 0. Now let's discuss about the standard state fugacity. Consider molar free energy of gas in two states, both at same temperature. Let G1 and G2 to be a free energy and F1 and F2 as the corresponding fugacity in this state. Then free energy that can be given by delta G is equal to G2 minus G1. So can say that RT ln F2 upon F1. How this equation becomes? Because we can say that G1 is equal to RT ln F1 and G2, which means RT ln F2. So if we are taking difference of these both, we can common the RT. So this is the RT ln. So can say that ln F2 minus ln F1. This becomes like this. So can write that ln F2 upon ln F1 into the RT. So this is how we can write this equation. So this equation becomes del G is equal to G2 minus G1 is equal to RT ln F2 upon F1. Fugacity is always equal to pressure at ideal condition, the standard state of real gas. The standard state of real gas at standard pressure at P naught. So if we are going to note the standard state of pressure, then we are going to denote by P naught, which behave ideally. So can say that P naught is equal to F naught for the standard state. So for ideal gas, free energy change given by del G2 upon, so this equation that can be replaced by pressure, and it becomes del G is equal to G2 minus G1 is equal to RT ln P2 upon P1. For ideal gas, P2 upon P1 is equal to F2 upon F1, or fugacity is directly proportional to pressure. But for real gas, fugacity is not equal to pressure. So ratio of fugacity to pressure for ideal gas is given by unity. Now let's discuss about the fugacity coefficient. The relation of fugacity to pressure is known as the fugacity coefficient. It's denoted by phi, and the definition of fugacity coefficient that can be given by phi is the ratio of fugacity upon pressure. So can say that phi is equal to fugacity upon pressure. So can say that pressure in real gas or effective pressure of particular component of real gas upon P. So can say that G minus G ideal, or can say that real gift free energy minus ideal gift free energy, that can be given by RT ln F upon P. So can say that G minus G ideal is equal to residual property, that can be RT into ln phi, where phi is the fugacity coefficient. So this is how the fugacity coefficient is represented. So this is all about the fugacity and fugacity coefficient. Now let's discuss about the fugacity in pure species and pure component. So fugacity for pure substance, that can be given by dg is equal to RT d ln f. Similarly, we may write fugacity in solution, that can be given by, for solution, gift free energy becomes partial molar gift free energy, so it becomes RT d ln f bar of particular component I. So this becomes partial molar gift free energy, or can say that fugacity in solution. But for ideal gas, F upon P is equal to 1. For non-ideal gas, lower pressure fugacity may replace two pressures. So we can write the equation F upon P is equal to 1 as the P tends to 0. Similarly, we can write for component I in solution, limit P tends to 0, partial molar fugacity or fugacity in solution upon pressure of particular component I in solution is equal to 1, or this is the partial pressure of particular component I is equal to 1. So this is how we can represent the fugacity in solution, where fugacity Fi bar is a fugacity of component I in solution and Pi is a partial pressure of component I. We know that partial pressure that can be given by Pi bar is equal to Yi P. So we can write Fi bar is equal to P Xi. Okay, so this becomes our fugacity in liquid solution, where Yi is a mole fraction of gas of component I and Xi is a mole fraction of liquid for component I. So this is about the fugacity in pure state and in solution. So this is about the fugacity in pure species and fugacity in solution. This is for fugacity in pure species and this is for fugacity in a solution. So this is all about today's lecture. I am completing my lecture here. Thank you.